right, today we are going to be talking graph interpretation. You are going to see something that you have seen before, but it's a good opportunity to review a couple of basic concepts since we are talking about graphs. So you can see a lot of learning goals there, but many of them are going to go. First thing we want to remember how to do is to determine if a given relation is a function. So a relation is a set of ordered pairs, so it doesn't always have to be a list of ordered pairs like you see here. It could be a graph, it could be a table, but any way that you see sets of ordered pairs is a relation. Domain, remember, of the relation is the set of the x values. And x values, we need to know, are also called the inputs. And because we're doing a lot of applications to real life situations and we're not always using x's and y's, we know that x is also called the independent variable. The range of the relation is the set of y values. We also call y values the outputs. So what you get when you put in a certain input, we call these the dependent variable because the value of y is dependent on what value we pick for our x. A relation will be a function if there's exactly one output for each input. So if you put 3 into the function 5 different times, you're going to get the same result every time. That's what it means that there's one output for each input. So first thing we want to look here in example 1 is look to see the domain. So domain x values are inputs. We want to list them in brackets because they're just single values in this case since we have ordered pairs. List them from least to greatest and don't repeat. If there's a repeated x value, just list it once. So here I've got -1, 0, 5, and 9, and those actually are already in increasing order. So these are the values for our domain. Our range, we've got 7, 1, 2, and 3. They're all different. List them in increasing order. So 1, 2, 3, and 7. And is it a function? Well, each x that we have is only assigned to a single y. There aren't any repeated x's. So yes, this has to be a function because each of my inputs only has one assigned output. So I would like for you to try number 2 and number 3. List the domain, the range, and determine if it's a function or not. And so pause it now to do that, and then unpause it when you're finished to check. So my domain here, I've got 6, 5, 5, 7. So 5, 6, and 7 are the domain values in increasing order. My range values, 6, 6, -2, 6, so -2 and 6 are my two ranges. So to determine if it's a function, I saw a repeated x. This 5 was repeated, so when that happens, I have to look. Was that input assigned to more than one output? And the answer is yes, it was. So this cannot be a function because your input 5 had two different outputs. One time I put in 5 and I got 6. One time I put in 5 and I got -2. So that means it cannot be a function. For number 3, my domain, my x values, I've got pi, 0, -2, and 4. So -2 is the smallest, then 0, then pi, and then 4. It's my domain. My range, 0, pi, 4, negative 2. It's the exact same. Is it a function? Well, I look at my x values. Pi, 0, negative 2, 4. I don't even repeat x values, so that means yes, this must be a function. Now, when we are looking at domain, range, and is it a function, when we're looking at a graph, the domain and range are going to be different. And we've talked about this before. We studied it a lot when we did our parabola parent graphs. And we did the domain and range two different ways. What we are going to do in this section is going to be interval notation. And so I put a note here that we use these parentheses if the endpoint or that particular value is not included. So these are like greater than and less than symbols. They don't include the endpoint. We use brackets if that endpoint is supposed to be included. So meaning if we want it to be like a greater than or equal to or less than or equal to. You should be familiar with the vertical line test. That's how we tell if something is a function when we're looking at its picture. No vertical line can intersect the graph in more than one point. All right, so I look at example 2, my domain, and it's hard to read on the screen, but look down at your paper and it's pretty easy to see that the x values go from right here to right here. And those domain values, if you look at your paper, that's -7 to 7. And that point is included. It does actually hit that point right here and right here. So that means I'm going to use the brackets. My domain goes on the left side from -7 all the way up to +7 on the right side. Do the same thing for my y values. My y values start here, that is included, and end here, which is also included. So from -1 to +7. Is it a function? No, because look, there it fails the vertical line test. I had a vertical line that touched in more than one spot. Here, my domain, if we look, my x values keep going because I've got arrows on both ends. So we used to say all real numbers. In interval notation, all real numbers means I go from -infinity to +infinity. We always use the parentheses on the infinity symbols because you can't include the number infinity. The range, it starts here, it includes that point. So when y is 2 is where my range starts, and it gets bigger. So going to infinity, 2 to infinity. Is it a function? Well, I've got all kinds of vertical lines. They're only touching once. So yes, it is a function. This one, my domain. Well, on the left side, it's got all kinds of negatives because of these arrows. So no limit on how negative it goes, so it starts at -infinity. As I move to the right, it stops right here at -1. So that's its highest x value, so that gets its bracket. The range, it's going to keep going down slowly this way, going to keep going up slowly this way, so that means the range is from -infinity to +infinity. Function test, nope. Fails the vertical line test. This vertical line touched twice, so did this one. All right, last one, domain, the x values that you see. Well, you only see one x value. You've got all kinds of points on it, but the only x value that's there, and if you look down, you can see it a little bit better. And it looks like the arrow, -2, 3, 4, 5, is at -1. So the domain value there is -1. Perhaps on my paper it looks like it's at -2. So I can't tell since the graph is so small, but if it looks like the vertical line is at -1, then the domain is -1. If it looks like the vertical line's at -2, then the domain is -2. So again, you choose based on what it looks like on your paper. The range, however, regardless of where that vertical line is on your paper, the range, it has arrows on both ends. It keeps going. So -infinity to infinity. Is it a function? No, it is a vertical line, so clearly it doesn't pass the vertical line test. All right, so that should be mostly review. What we're going to do now is we're going to look at some graphs that you studied in science, either in junior high or maybe ninth grade, you'll study them, but both distance time and speed time graphs, because it's really important when we apply things to real life situations to be able to interpret the graph. So a distance time graph tells us how far an object moved. So when we did the parabolas, where you were shooting something in the air, distance was your y-axis and time was your x-axis. So those were distance time graphs. And when you're looking at a distance time graph, the steeper the graph is, the faster the motion is. It's very fast motion if it's a very steep graph. A horizontal line means the object is not changing its position. So that means the object is at rest. Downward sloping line means that it's returning to the start, going back down to the ground maybe, or wherever it is it started, it's going back down. So going up means it's traveling somewhere, traveling a distance. Going down means it's coming back to where it started from. Steeper lines means it's a fast speed. Then you can see that a parabola means that it's increasing. It's not a steady speed, but it's increasing speed. Now, it's really important that you pay attention to the labels that you get, because if you're looking at a speed time graph instead of a distance time graph, that changes everything. Speed time shows how the speed of a moving object is changing. So here, the steeper the graph is, it doesn't mean that it's faster motion than something else. It means that that's greater acceleration, meaning it's getting faster more quickly. So greater acceleration when you see steepness on a speed time. A horizontal line on a speed time graph doesn't mean that the object is at rest. It means that it's moving at a constant rate. So whatever speed it was at, it's maintaining that speed. So horizontal lines means steady speed. Downward sloping line means that the object is slowing down or decelerating. And so I've got these little graphs here that you can refer to that should kind of help you remember on speed time and distance time what each of those types of things mean. So you can see here a gradual acceleration, here's a more quick acceleration, here's steady speed, here's steady deceleration, slowing down. So until you get the hang of it, you can refer to those as needed. All right, so let's use some of this now. Distance time graph represents the position of an object that's moving in a straight line. So it's moving a distance. We know that it's moving in a straight line according to the directions. So we want to explain what is happening during each interval. So the first interval they give us is from 0 to 2 seconds. From 0 to 2, I've got a line with a positive slope. And we learned up here that on distance time, a positive slope going upward means that we are having a steady speed. So we are traveling somewhere, we're going somewhere, traveling away from the start. Now, because we have actual labels here, we don't have to just say steady speed. We need to be as specific as possible. On this little unit right here, it went 10 meters in 2 seconds. So that means we can say what the speed was. So if it's 10 meters in 2 seconds, that's 5 meters per second. So traveling away at 5 meters per second. Then we have a change from 2 to 4 seconds, which is this interval right here. It's still traveling away. It's traveling away faster than it was before. And again, we can find its speed. That's another 2 seconds that passed, and it went an additional 10, 20 meters. So 20 meters in 2 seconds means that now it's traveling at 10 meters per second. And then, finally, from 4 to 6 seconds, right here, horizontal line means that it's stopped. And where did it stop? 30 meters away from where it started. So that is our interpretation of each of those little intervals. Next, example 4. It says Kendra is speeding along a highway and is stopped by a police officer. The officer gives her a ticket and then she continues on her way. Graph time on the horizontal axis and her speed on the vertical axis. I can't write sideways because I can't turn my paper, so I'm just going to label speed this way. Okay, so speed time. Let's think back at what things mean. So here, if we're going up, that means we're accelerating. We're getting faster. If we have a horizontal line, that means we're traveling at a steady, constant speed. So it says Kendra's speeding along the highway. So she's traveling at a relatively fast, because it says she's speeding, so we'll put it somewhere near the top. Yours doesn't have to be exactly where mine was. But she's speeding along, and then it says she's stopped by a police officer. If you're stopped by a police officer, you're going to slow down relatively quickly, and you're going to come to a stop. So we slow down, and we come to a stop. Then we are staying stopped, so along the 0 acceleration line while she gets her ticket. Then it says then she continues on her way. So she's going to accelerate, we assume, and hopefully not reach the same speed she was at before. So this would be an example of how we can take a situation and draw something that represents it. Again, if you were drawing this, you wouldn't have to have your speed at the exact same line as mine. Maybe yours is up here. You wouldn't have to necessarily slow down as fast as I did, or you could slow down faster, but that is going to represent what's happening. Example 5, it says the following graph represents the percentage of the U.S. population P that is foreign born, so born somewhere else other than the United States, and it's representing T years after 1970. All right, so again, really important that we learn how to interpret important parts of the graph. So it says here, what year is represented by T equals 0? Well, it says T years after 1970. So if T is 0, that means it's 0 years after 1970. So the first question's answer is 1970. Then it says, how is this related to the vertical intercept? Notice it doesn't say y-intercept because we're not using y as our variable. It's p. So the vertical intercept is right here. So the vertical intercept is right here. We want to know how 1970 is related to that. Well, T is the year, so in 1970, what does P stand for? It says that P represents the percentage of the population that is foreign born. So that means that the vertical intercept represents the foreign born, oops, doesn't look like a B, population percent in 1970. It says label the part of the graph which represents a decrease over time in the percentage of U.S. population that is foreign born. So where is the percentage decreasing is what it wants to know. So I can use color here, but it decreases all the way along here. So there's our part B. We labeled the decrease. Then it wants to know when we have increase. Label the part of the graph which represents an increase over time. So that would be on the other side. This is an increase. Label the part of the graph which represents the lowest percentage of U.S. population being foreign born. So that would obviously be at the bottom. So that's the lowest percentage. Provide an explanation for the lack of horizontal intercept. So, why does my P not touch my T axis? Think about what that would mean. If it goes down and its P value is 0, that means that at a specific time, the foreign-born population would have to be 0, which is never going to happen in this country. So we can just say if the graph crossed the horizontal axis, that would mean that 0% of the population was foreign born, which is never going to happen. All right, last one. Richard types for 3 minutes at a rate of 35 words per minute. He takes a 2-minute break and then types for 3 more minutes at a rate of 20 words per minute. Which graph represents Richard's time at the computer? So this is a speed time. So this 2-minute break means that there should be some flatness in the middle. So for the first 3 minutes, he's typing at the same rate. So if we look at all of these, at 3 minutes we have a change. So we need to see which one is representing the correct amount of words per minute. So if he's typing for 3 minutes at 35 words per minute, so 35 words per minute times 3 minutes, that means at the end of 3 minutes, he should have gotten to 105 words. So I look at 3 minutes, which graph has 105 words? Well, this one has like more than 120, maybe 130-ish. This one has like 30, that's not right. This one has 60, so that can't be right. So I don't even need to look necessarily at the rest of them, because this is the only one that has 105 words. Now check the rest of the graph, because in 3 minutes in, we get to what could be 105 words, because right in the middle would be 100, and it's just a little above that. Then There's a time where he's not typing. So he's staying at 105 words for a 2-minute break. And that break is 2 minutes long. It's from 3 to 5 minutes. Then it says he types for 3 more minutes. So yes, from 5 minutes to 8 minutes at a rate of 20 words per minute. So that means that he should be 20 times 3, adding 60 more words. So from 105 to 165, which is where this ends up. So we have confirmed that D is the correct choice. All right, that is it for today.